Welcome, one and all, to the Cool Worlds podcast with me, your host, David Kipping. So, first off, it has been a little while since we posted our most recent podcast episode, and that's on me. I apologize for that. It has been a bit of a crazy couple of months. We had the holiday season, Christmas season, of course, which if you have young kids like me at home, you know that that is not going to be the most conducive audio environment for trying to make podcasts. So that's part of the excuse. And of course, when January came around, which is the start of semester here, always a busy time teaching new classes, things like this. But on top of that, my major work over January has been, frankly, reading applications. Every year we admit new students to join our PhD program. Just the PhD program, of course, there's also the undergraduate program, but even the PhD program has been an enormous amount of work for me. We've had over 320 applications this year for what will probably only be like 4 or 5 students we eventually actually have join our PhD program here. That's kind of bizarre, right? The odds are almost 100 to 1 at this point for admission into these programs. And this is a trend which is happening across the country in not just the major schools, but even the smaller schools in astronomy. So I'm kind of confused by that. It's interesting. Astronomy seems to be outpacing physics, STEM degrees, engineering degrees in terms of its attractiveness, its competitiveness. And it does mean that those top students that we're admitting, they're off the chart. They have multiple papers already, some of them. They are like captain of the tennis team. They've won like chess tournaments in Russia, and they're just kind of phenomenal students. And it makes you think like, wow, how's this going to be in another 10 years from now at this rate? And would I have even got into graduate school given how outrageously competitive it has become? It does mean, on the other hand, that it has become a lot more work for us on the other side. To read all these applications and try and judge them. The top 50 of these applications are frankly all good enough that you could basically admit them without concern. But of course, that's too many. We can't possibly fund that many students. There's not enough research money in our department to do that. So we have to select down, and that process is really tough. And so that's what I've been doing. It's been a lot of work, but I feel good about the final class that we've admitted, and hopefully that means with that out of the way, we can get back to making more videos and podcasts and things like that. So with that in mind, who's our new guest today? This week I have Dr. Viraj Pandya. So Dr. Viraj Pandya, he did his PhD at UC Santa Cruz, and he is now at Columbia. So he's just a couple of offices down. I think he's probably going to have the record for the smallest commute of any guest that we'll ever have on the podcast. He's literally you can probably hear me talking right now, introducing him. So he's a Hubble Fellow, which is these very competitive national fellowships issued by NASA, and he's here, and he's working on galaxy formation, and particularly the earliest galaxies in the universe. And what we're going to be talking about in today's episode is JWST, this incredible 6.5 meter telescope, which is just revolutionizing our view of the early universe, but also true of the nearby universe of exoplanets. But in particular, you've probably been seeing this in the news, that JWST is kind of really shaking up how we think about how early galaxies formed and evolved, and in particular their shapes and the timing at which they emerge. It all seems very surprising. So Viraj actually had his work highlighted in the New York Times quite recently, in January. In fact, he was on the front page. Well, not his face, but his work was on the front page of the New York Times, which is very rare. Scientists don't appear on the front page of the New York Times too often. So that's pretty amazing, and it's well deserved, because the work he's been doing has been pretty incredible in terms of the implications that it has for how we think about galaxies. It's really shaking up the textbook, as you'll hear about today. So the title of his paper was Galaxies Gone Bananas. And I think as we get into the discussion today, you will just see how profoundly surprising the results are, and how that phrase is both true in a figurative and even a literal sense. When you look at these galaxies, they actually do kind of look a little bit bananas. So we'll get into that today. I hope you'll enjoy this discussion, and I'll see you in the back end. Viraj, thank you so much for joining me today. It's really exciting to get you into the Cool Worlds podcast, especially because you've been in the news recently. So thank you for joining me.
Yeah, thank you so much, David. It's great to be here.
So obviously your work is on galaxies.
Yep.
And I thought, just to set the scene for everybody at home so we can all be on the same page, why don't we start by talking a little bit about the canonical story of galaxy formation. Now, certainly when I was looking through the old classical textbooks of how galaxy formation was thought about, there are a lot of analogies to think about the solar system, actually.
Yeah.
The solar system has a coplanar disk. It's kind of two-dimensional, but in the center you have a central mass, and everything goes around it. And that's kind of similar to the Milky Way. Yep. We have a disk. We have all these objects in orbit of it, essentially. Not perfectly circular orbits, but not too far off either. And in the middle, you have Sagittarius A star, which is like 4 million solar masses. And around that, you have something like 100 billion stars in orbit. So they seem like disks. The universe wants to make disks.
Yeah.
So why? Where are these disks coming from? And how do we understand the population of modern galaxies that we see around us?
Yeah, that's a great analogy to planet formation and star formation. So yeah, the Milky Way is a disk, and as you're alluding to, there's this idea that the solar system was formed out of a gas cloud, roughly spherical, like the Laplace's nebular hypothesis, and it had initially very small amounts of net rotation, but as it collapsed due to the force of gravity, it sped up. Right, because conservation of angular momentum, and it flattened into a disk. And so there's actually a very simple analogy, straightforward, to galactic disk formation. So the picture that we have in mind, and that actually, like my own models of galaxy formation currently encapsulate, is very similarly, the Milky Way at some point was formed out of a proto-galactic gas cloud that was roughly spherical-ish in shape, much larger scale, like maybe 100 times larger than the Milky Way today, and it had small amounts of net rotation. But then as it collapsed under the weight of its own gravity, it started to speed up because of conservation of angular momentum, and it formed this disk.
So it's kind of like the pizza pie effect, right?
Exactly.
If you see someone spinning pizza, it spreads out.
Exactly. In fact, the analogy that I've been using, with this new work is, I say, when you look out into the local universe, like Hubble did 100 years ago, right? You see galaxies that look like pizza pies, right? Disks. You see galaxies that look like balls of dough, perfectly round balls of dough in 3D. These are the elliptical galaxies. And those are really the two main types that we see nearby. Then you have some kind of a mixture of those two, where you have like a dough ball at the center of a pizza pie. So like a bulge at the center of the disk, like we have for the Milky Way.
Okay.
Yeah.
Now, the ellipticals, then, they don't follow this story. And I have to say, the name elliptical seems like a misnomer, right?
Yeah.
Because if they're just these kind of quasi-spheroids,
Yeah.
it's like so many things in astronomy, like planetary nebulae.
Yeah.
Like, why do we call it that? It's
Yeah.
just a historical hangover, and we're all kind of stuck with this silly name. But ellipticals, maybe you can explain why are they called ellipticals, and where they don't fit into this story of Laplace nebula spinning pizza pies. So where do they come from?
Yeah, so that's another great point. So ellipticals, Hubble came up with this terminology, and part of the reason for this is that he saw that for some of the brightest nearby galaxies that he cataloged 100 years ago, there was a substantial fraction of galaxies that appeared rounder, like relatively round or circular in projection, many more in excess than you would expect if you just had a bunch of pizzas that you were looking at in space randomly oriented. In that case, you would see roughly equal numbers of pizzas face on and roughly equal numbers of pizzas edge on and in between. But he saw many more rounder things. So he hypothesized that there must be an intrinsically round, spheroidal class of galaxies, the ellipticals, that would preferentially appear round. Now, the ellipticals still also can appear elliptical in projection, right? They can appear heavily flattened because there are some ellipticals that are heavily flattened. And it wasn't until, 80, 90 years after Hubble's 1926 Astrophysical Journal article that we really started to get constraints on the orbits of the stars in these elliptical galaxies, and we found that the stars in these elliptical galaxies are on kind of random orbits, kind of just all in many different directions. Whereas, as you said, for disk galaxies like the Milky Way, the stars are on circular orbits in like a plane, more or less.
So these kind of look more like, they're not perfect spheres, obviously, then.
That's right.
If you sometimes see them elliptical.
Yeah.
So is it more like an American football or a rugby ball, then you kind of get this kind of prolate spheroid?
Yeah. So some of them are relatively prolate. We now know that the most massive, the brightest ellipticals nearby, they truly are relatively like round in 3D. And then as you go to like some of the lower mass ellipticals, maybe like a factor of 5 to 10 more massive than our own galaxy, these we think are an extension of these football-shaped things. We call the S0s or the lenticular galaxies, which are like these bulges within disks.
Okay.
Now, how do these ellipticals form? So that's still, debated. But to connect back to the nebular hypothesis, the standard story is the first things to form galactic structures are these disks, because they form out of these collapsing gas clouds that spin up and flatten out. And then you can have disks that merge with each other. And when they merge with each other, they can destroy, some of the disk structure in the progenitor galaxies, and you end up with this remnant that is going to have some amount of bulge growth, some amount of this central, concentration of mass, where some of the stars are on these relatively random velocities, orbits. And how exactly, what the remnant looks like, what fraction of the remnant in terms of mass or size or light is going to be in this bulge, this like little elliptical thing, the center, versus what is in the extended disk. That really depends on the properties of the progenitors, like how much gas was there in the progenitors, which can then fuel like subsequent star formation in a disk or at the center as well.
But as a proxy, then a nascent first generation galaxy would have very little bulge.
Yeah.
But then the more mergers, the larger the bulge, until eventually that bulge essentially swells and it becomes what we'd normally call an elliptical galaxy. Is that kind of the picture? Or at least canonically?
That's the canonical picture, where mergers cause the growth of bulges, and eventually when you have mergers of lots and lots of mergers in the history of a galaxy, then you've kind of destroyed, the possibility for it to have these stars in these nice circular orbits, and you end up with this roughly kind of bulge-dominated, in the case of ellipticals, pure bulge systems. Yeah. Now, there's some nuances here because there are other ways to form bulges, like instabilities in the underlying disk due to gravitational effects and things like that. But
I have to say, as an aside, Galaxies is obviously a little bit different to exoplanets, but I've always found it fascinating. And the thought that there are these trillion star galaxies out there, or even more than that, these massive ellipticals. Yeah. And there's also tiny, tiny galaxies that are in orbit of the Milky Way, of course, like the Large Magellanic Cloud. And it makes you wonder about what it would be like to be born in these different galaxies, and whether life or civilizations happen differently in these different circumstances. Was what kind of got you interested in this subject? Was it something sci-fi like that, or was it just more the hard science of their underpinnings and their origins?
So it's definitely the latter. It's all of the above. But for me, I really want to answer this question: how did we get here? And NASA actually has two programs that are designed to try to answer the same question. One is the Cosmic Origins Division, headquartered at Goddard. And the other is this program called the Hubble Fellowship postdoctoral program, which is, so I'm a Hubble Fellow here. And so the research that I do tries to get at this question of how do we get here? And so part of that for me is figuring out, we have the galaxy, the Milky Way today that we live in, and what did it look like, 10 billion years ago? And what were the conditions of the Milky Way when, say, for example, the solar system formed, right? 5 billion years ago or so.
And where do we come from? And just to put a pin on that, you've come two offices down. So you are the record for the shortest commute podcast guest we've ever had. Yeah. But maybe that'll be a record that will be broken one day. I don't know, but that's awesome. Yeah. But I guess I am curious, just to push back on that a little bit more. Like, surely as a child, you were not thinking, oh, NASA have like got this section in their horizons that really cares about.
Yeah.
That can't have been your inspiration.
No,
Like
no.
what, I mean, maybe it makes sense that, you know, there's a whole field that's, and it feels exciting because there's so much research happening in that area now as a mature scientist. But did you discover then your love for galaxies later, or was there an interest earlier on?
Yeah, so actually my discovery of astronomy as a science was way later on, actually near the end of undergrad. So my degree, my bachelor's degree from Rutgers, is actually in economics and math.
Okay.
And halfway through undergrad, you know, I was taking my econ courses and some math courses, and I just randomly discovered Carl Sagan on YouTube.
Down
Watching,
the rabbit hole.
yeah, Pale Blue Dot and Cosmos clips and Neil deGrasse Tyson, right, Bill Nye.
Yeah.
And I was like, oh wow, there's this entire science of astronomy, and I remember thinking, you know, there's like all these things happening in the world that still happen today, wars and things like that, and wow, you know, with astronomy we can really focus on things that are at a higher level. Maybe, you know, it's a path to peace at some point. Convince people in the world that there's other stuff to think about.
Bigger perspective.
Yeah, exactly. Yeah. So I started the Rutgers Astronomical Society because there was no astronomy club at the State University of New Jersey.
Wow.
And through that, I got to meet professors of astronomy at Rutgers, Saurabh Jha, Rachel Somerville, Tad Pryor, and others. And through them, I actually got involved in research in astronomy before I'd taken any like the basic physics courses. Huh. So I was studying, you know, how galaxies change their shapes and colors before I had any idea what angular momentum was, right? That actually, I think, helped me kind of stay in the field and kind of push through, because, you know, I think there are a lot of things that academia does great, but one of the things is that, you know, this process of trying to learn and hone your creativity and passion for a field, you know, you go through like the usual courses, they can really beat that excitement out of you. And so I'm glad I got to do research before taking classes, and I got lucky. I went to Princeton as one of the first bridge students there. It's a program that for people that wanted to switch from something else to astronomy. And so in my case, from econ to astro. And really more of the same there. You know, I just did a lot of research. I took the classes that I needed on my transcript and then applied to grad school.
What do your parents say to that, switching from, because
parents,
econ is like a standard, like,
I know.
there's a good
like,
paycheck at the end of this one, I'm going
like,
to go to astronomy.
This guy, just like, like, why? What are you doing? Like, I mean, even, you know, even a little bit to this day, like, you know, been on the front page of the New York Times, but it's still like, well, okay, when are you going to get a real job?
Yeah, well, there's time for that down the road. Yeah, that's interesting. I kind of feel the same way about research. I think when I was an undergraduate taking classes, I didn't do it quite reverse like you did. I was more kind of conventional, that I always did love astronomy. But I think my love for astronomy almost waned when I was taking some classes, just because it was so theoretical and hypothetical almost, and abstract. I did mine at Cambridge, and we didn't once look through the telescope at Cambridge. Just that's not part of the program at all. So it's very, very like disconnected almost. It's just the math, which is enjoyable, but it's not the same. And it was only when I did research that, I think it's a transformative experience. So that's when I discovered this is what I want to do. So it seems like a good lesson then for people who are thinking of astronomy. But just to try a research project. Yeah.
I mean, I think the best way to learn something is to get your hands dirty and really, you know, build something. In this case, for astronomy, a lot of what we do is we build code infrastructure, right? To like analyze some catalogs or analyze some images. You can also, there's, you know, instrumentation projects that you can get your hands dirty with, or pencil and paper theory and things like that. So
So let's, from a little segue into the origins of us as astronomers, the origins of galaxies. Let's come back to that. So we have this picture that seems, it's so often, it's also true in exoplanets as well, that we really thought everything was wrapped up. We thought we understood everything from this simple nebula hypothesis, and we were pretty sure every planetary system would look just like our own planetary system. And then when you look around, things look different. In the local universe, maybe things don't look too different, but as you look further and further away, of course, you're looking back in time. And there was this survey that Hubble did called CANDLES, and I had to look at what this stands for. It's the Cosmic Assembly Near Infrared Deep Extragalactic Legacy Survey. Just
Yes,
rolls off the tongue.
That's
CANDLES.
right. Yeah, candle spelled incorrectly. Yeah.
Yeah, it doesn't
Google
even
it.
make sense. But infrared, yeah, anyway.
Yeah.
So this happened around 2011. And they were looking at redshifts between 1.5 and 8. And that's really a measure of how far back in time you're going. So using my cosmic calculator, that turns to about 600 million years for the age of the universe at the youngest end, to about 4.3 billion years.
That's right.
So we're not in the very earliest stages, but the part where we really would expect galaxies to have formed by this point. And so CANDLES was a really historic survey, and it led to some surprises in terms of the shapes. Now, maybe this is a good preview for what you're going to talk about with the James Webb. What did Hubble find that already kind of teed this up a little bit?
Yeah. So CANDLES actually, so yeah, you're right. It was one of the largest programs ever undertaken with the Hubble Space Telescope. Almost 1,000 orbits dedicated just to this one Treasury program. And it really, we always hear about the Hubble Deep Field, but CANDLES was the program that expanded that to 5 deep fields. So there's 5 fields, very tiny, a fraction of the full moon on the sky, on different parts of the sky, where astronomers, pointed the Hubble Space Telescope and got, 2 months worth of observing time on. And one of the things that they found is for galaxies that were blue, that were forming stars, that existed about 10 billion years ago, so redshift of about 2, where the stellar masses of these things were about a factor of 10 lower than the Milky Way stellar mass today, so the total mass in stars. So aka, for galaxies that were Milky Way ancestors, CANDLES found that there were many of them that looked elongated. They looked like linear, clumpy structures projected on the sky. And actually, this was building on work that was done in the mid-90s. So there were astronomers in the mid-90s, like Sidney Vandenberg, Lennox Cowie, Bob Williams, and many others, that started to plan the very first Hubble Deep Fields, the proto-Hubble Deep Fields. And back in the 90s, they were using instruments on Hubble that looked at ultraviolet or optical parts of the electromagnetic spectrum. And so when you're looking at galaxies that existed 10 billion years ago, the light from them that is now reaching you, originally when it was emitted by like the parts of these galaxies where stars were forming, new stars are forming. So you're getting some biased view of these early galaxies. And they too found that galaxies appeared linear. And so with the CANDLES survey, it used the Wide Field Camera 3, a relatively new instrument that was installed in 2009, I believe.
Yeah, I think Mike Massimino, who's faculty here in engineering, actually was one of the astronauts who installed it.
Yes, that's right. Yeah. And so that instrument looks at near infrared wavelengths. And so it can capture the light emitted from these distant galaxies that was emitted by the bulk of their older stars, not just like the young, blue, biased star population. And even at these redder wavelengths, where you're seeing the bulk of the body of the galaxies at these early times, there were also lots and lots of elongated ones. And did they believe that, or did they think it was a some kind of perspective effect, geometry effect, or something, a bias? What did they think at the time? So there's really kind of 2 camps of astronomers, even to this day. So there's one camp which, rightly says, well, let's take the safest approach. I think, we think that there's some kind of bias. So, people have shown that in the local universe, there are extremely faint and thin disk galaxies. They call them low surface brightness disks. And we see them in various orientations. So you see, lots of ones edge on, you see lots of ones face on, and you see them in between, different orientations in between. Why are they so dim? Just far away, or just few stars? What's going on? Few stars, and also very large sizes. Just very diffuse. Very diffuse, exactly. And so the idea was, well, you're seeing lots and lots of these elongated looking galaxies in the distant universe, because the edge-on ones are the ones that you're seeing preferentially. They're the ones where the light is concentrated to this plane. It's relatively bright, and so they're easier to detect in your survey, in your Hubble imaging.
Right.
And you're just not seeing the rounder ones, right? The deficit of rounder ones is because when you see one of these things face on, the light is more spread out, and so
they're all the same shape in this picture, right? They're all basically disks, but the ones that are face onto you, the number of stars per pixel is essentially just too low to be detected. But if you put that edge on, now you're seeing along the columns, you get all of those stars in one pixel, so suddenly this thing pops up and you can get a nice image of it.
Exactly.
So that was the hypothesis.
That's right. That's right.
Okay.
And that makes sense, right? I mean, you want to try to explain your observations in a way that is kind of consistent with, your current understanding, of galaxy formation in this context. So that's one side of the argument, right? There's like some kind of detection bias. We call them a surface brightness selection effect. You're just not sensitive to the face-on faint ones, and you're seeing lots of the edge-on ones. The other side of the argument, which is what actually the Candles team proposed, led by Arjen van der Wel in a 2014 paper, my colleague, is no, there actually is some intrinsic 3D geometrical evolution, in the sense that you're seeing lots and lots of the edge-on ones because these galaxies intrinsically are flattened along a second axis. So they really are not all just, circular disks like the Milky Way, for example.
So you've squished the Milky Way in another dimension. Yeah. So I think I've seen the word pickle being used at that
pickle
time.
is one. My other
pickle-shaped galaxies.
Yeah, I mean, we're in New York City, so my other analogy that I use is, I started in the beginning, I said balls of dough are ellipticals. Yeah. You take a ball of dough, flatten it along one dimension, you get the greatest thing in the universe. Pizza. Yeah. Now take a pizza, flatten it along one of the two axes, you get my other favorite thing in the entire universe.
Baguette?
A baguette.
Oh,
yes.
nice.
Yeah,
there we go.
Exactly.
Okay.
Yeah.
Well, that's kind of French, so I wasn't expecting that to be a New York connection. But
I say breadstick, but
yeah. It's all food related.
Yes, exactly.
Okay. Yeah, good. But that makes sense. So, but very peculiar, I suppose, because that doesn't fit, at least with the ellipticals and the disks. You're like, that's okay because we can make the ellipticals from the disks, but these pickles, these baguettes, that's like literally who ordered that?
Literally, it's a brand new class of galaxies, right? And we don't see these things in local. I mean, in extreme environments, like huge clusters of galaxies, which are like the New York cities of the galaxies where they all congregate. You might see these pickle-shaped things, but that's because they've been tidally kind of disturbed by interactions with other systems usually. And we also we don't observe them in such large numbers as Candles suggested back then. So there was a lot of kind of I'm not even sure I want to say pushback, but it was just like we just don't talk about it.
We don't sure what to make of it.
Yeah, we don't talk about it. I mean, it's and there's different techniques, right? The techniques that are used to come at this result that early galaxies may have started out shaped like breadsticks or pickles, or to throw something else in, cigars. That technique is fundamentally different from the techniques that we use to by eye classify galaxies. Like, by eye, I can say, okay, this thing looks like a disk, or I can look for, you can measure the intensity of light and how fast it falls off from the center of the galaxy. And for disks in the local universe, and many, at higher redshifts that we've observed that we think really are disks because we've observed like the motions of stars in them, the light falls off exponentially with radius. That's a necessary but not sufficient condition for saying something is definitely a disk, because it turns out that a lot of these pickle-shaped things, their light also can fall off exponentially in projection. So you need something else, and I have something in mind. But we can come back to that later.
Let's come back to that. Before we get into JWST, because obviously Hubble is a 2.4 meter class telescope and JWST is 6.5. So I think that's the immediate question, is what does this much more powerful telescope give? But maybe we can just set the scene about the state of the universe at this time. Like what was different? What should people keep in mind about the early universe versus how we think about the modern universe? What were the conditions like?
Yeah, so great question. So in the early universe, the conditions were dramatically different. So, you have the densities of like the intergalactic medium and even the interstellar medium. The densities overall are just much higher because the universe, has not expanded to the state that it's in today. So you have much higher densities within and around galaxies. You also have and as a result, relatedly, you have a much tighter, denser cosmic web of dark matter, which forms the skeletal backbone of the universe, right? These like filaments of dark matter, which eventually kind of intersect at nodes, which is where the clusters of galaxies will eventually form. And, it depends what exact epoch you're looking at, but at very early times, the universe, we call it say it's in the dark ages because a lot of the stars haven't formed yet, and the stars and the black holes that are accreting, they're the machines that generate this prodigious amount of light that then can blow holes and ionize this intergalactic medium. And then at slightly lower redshifts, we call it the cosmic noon, redshift 2, when we think, for example, the Milky Way reached its peak rate at which it was forming stars, new stars. And so if you're forming so many stars at cosmic noon, then this is the epoch right after the dark ages where, there's just lots and lots of ionizing radiation, photons, light, just traversing the universe. And that can affect the kind of structures that can form.
And these stars are obviously forming from more pristine gas than we have today, which has been contaminated with metals and enriched elements.
That's right.
But I assume we're not at the point where we have population of 3 stars in your galaxies. You're probably past that point.
Yeah, we're past that. Yeah.
The stars that you're seeing are intrinsically familiar-ish to the types of stars that we have today.
Yeah.
Okay.
Yeah, exactly. They're like the earlier progenitors of like the modern population 1 and 2 stars.
And so you said that the bluer maybe, and that blueness is just because of the fact they're younger means if there is a more massive star that forms, it will be bluer.
That's right.
Because it's hotter. Yeah. And therefore those stars are still around, but as you go forward in time, those stars die off. And so you get an overall redder and redder galaxy.
Yeah, and you just have lots and lots of star formation. So you have lots and lots of these young, hot blue stars that can outshine the older, less dominant, redder star population.
And does that make it difficult to pin down the redshift then? Because when you're pinning down the redshift of a star, of a galaxy, that's all it's about, its color. Yeah. If these galaxies are intrinsically bluer anyway, could that, you need to somehow account for that, you would think, in your distance measurement. How do you guys deal with the precise redshift measurements?
Yeah, that's a really good point. So most of these galaxies, the redshifts come from, we have like 20 to 40 band photometry, which is essentially what is the flux, how bright is this galaxy across a huge part of the electromagnetic spectrum. And when you measure that out, the brightness is a function of wavelength or frequency. You get a particular shape. We call this a spectral energy distribution. And then you compare that observed shape for the brightness of this galaxy at different wavelengths to a huge library of templates of galaxies where we think we know their internal stellar populations. How will that manifest in some different shape for the observed spectral energy distribution? So in essence, for our galaxies, we're not in the POP3 regime. We're pretty confident in we call it the photometric redshift, and the typical estimate that we have for the total mass in stars.
I should say if we use POP3 and maybe we use it too nonchalantly there. Yeah. Those are the very first stars that form the universe. Which there are people with JWST hoping to find those as well, but almost a separate topic, to be honest. Right. So in that sense, you've and all this 20 band data. This is all from, I guess, in the case of candles, that would all be from the Hubble Wide Field Camera 3. So that's all near infrared.
That's right.
Data.
Well, and as well as some UV, because you have the advanced camera for surveys, ACS.
Okay.
And the WFC3 also actually goes into the UV.
Oh, I didn't know that.
Yeah,
Interesting.
there's a UVis channel.
Wow. Yeah, exoplanet people use it all the time, but it's mostly used for near infrared.
Yeah,
so
near infrared is where
yeah,
it's
interesting.
Yeah.
So let's leave Hubble and go into the JWST world.
Yeah.
So just like candles, there has been another survey with JWST. Again, a nice acronym here. So it's called SEERS. Am I saying that right? Or
That's
Keers?
right. SEERS.
SEERS.
Yeah. Yep.
Kind of reminds me of the isn't it like a furniture store in the US called SEERS or something?
Yes, I used to
Or
go to when I was a kid.
store.
Yeah.
Yeah. Okay. So I'm a Brit, so I don't know what these stores.
Spelled
but
a little differently, but it sounds the same.
Yeah. So this is the Cosmic Evolution Early Release Science Survey.
That's right.
Tell us a little bit about that survey. What's it doing? What distinguishes it from candles?
Yeah. So SEERS, so the PI of SEERS is Steve Finkelstein. He's a professor at UT Austin, who I know very well because when I was a grad student at the University of California, Santa Cruz, as a first-year grad student, the co-PI of candles, Sandy Faber, famous for the Faber-Jackson relation for elliptical galaxies, she arranged for me to shadow Steve when he was chosen and as he was then putting together the SEERS collaboration, which was actually like a follow-on from candles. So there were all these people. Candles was like a multi-100-person collaboration. And so you have all this expertise, and people wanted to use that expertise, retain it, use it to then plan the new generation of surveys with James Webb. And back in 2016, 2017, NASA put out a call for early release science proposals, where the idea was about 10 teams would get chosen to become, some of the first teams to get data from James Webb, and on a very quick turnaround time, process the data, maybe show and release code for the community to show them, what problems that they run into, and finally provide, reduced, processed imaging, data, catalogs for the community to do science. So SEERS was chosen as one of these teams. It was very cool to see Steve put this together and then lead it. In the 6 years it would take to finally get the data, right? In 2021, we finally got our observations.
Of course, because all the delays, people were hoping
right.
it wouldn't be that long.
It was supposed to be in 2018 when I was in grad school, and then it eventually became 2021 and then 2022 when we finally got the data. So anyway, SEERS, it's comprised of a lot of people from candles, and what it's doing is, I mentioned candles surveyed 5 deep fields. One of these 5 deep fields, called the Extended Groth Strip, is...
Extended what, sorry?
Extended Groth.
Groth?
Yeah, named after Ed Groth. Yeah, professor at Princeton. Yeah,
okay.
So, EGS is what we just call it in short. So this is a long rectangular field that is right next to the Big Dipper on the sky. And so SEERS targeted EGS, roughly half of the Extended Groth Strip, to get multi-band imaging and spectroscopy over roughly half of this long rectangular field. And so we got data in like 6 or 7 different filters with NearCam. We got data with the redder instrument called MIRI. And then we use these instruments in parallel and with different observing modes to get spectra and imaging.
So it's a smaller patch of the sky.
It's a smaller patch
than candles because it's the early release. It's like
exactly
we're just doing a little shakedown thing.
Yeah, it's like a proof of concept. Like what can Webb really do?
Yeah.
So and then the crazy thing is, so candles, as I mentioned, it's the deepest survey. So 1,000 orbits on Hubble, and in some of these fields, you're kind of staring at the same patch of sky for several tens of hours to maybe days. And so when the first Webb data from SEERS came in, we were staring at this data, and it was amazing because SEERS, the field of view of JWST and Hubble is much smaller than the size of these little, like the Hubble Deep Field or these Aegis in this case. So you have to tile multiple observations together to get a mosaic, and any individual tile of this mosaic, SEERS only observed for less than an hour with Webb. But the images that it got in 10 times less observing time were just blew the Hubble imaging from candles out of the water. Like
Wow.
you could see so much more substructure in the same galaxies that Hubble observed, where it just looked like a noisy splotch.
Yeah.
And here you see like this nice kind of, like underlying low surface brightness extended components around galaxies and stuff. So this is great because this is the kind of data that we need, right, to answer this question. Going back to the puzzle of like, well, was Hubble just missing all of these face-on, low surface brightness disks because it wasn't sensitive enough, or was it actually, did Hubble find something?
Yeah, and of course that's just a nice kind of prelude to what might come, because as you said, this is 10 times less observing time than what Hubble spent.
Yeah.
By the way, one orbit of Hubble is 90 minutes, right? So
That's right.
There's 1,000 hours. That's 1,000 orbits is 1,500 hours roughly.
Yeah.
And JWST can also observe. I think it's true. Like it collects more data per unit time than Hubble because it doesn't orbit the Earth, and so you don't get these blackouts when you're behind the Earth or something.
Yeah.
So yeah, the potential then is really exciting. Of course, people are talking about JWST could last for like 20 years or something.
Yeah.
So
it blows my mind that, just trying to think of like a JWST deep field compared to like a Hubble deep field. Like,
yeah,
wow.
that's something to hang up on this wall when we get one of those.
Yeah.
That's for sure.
Yeah.
So let's talk about your work with this survey with SEERS.
Yeah.
And you, as I said, you're on the New York Times on January the 5th.
Yeah.
I should have asked you to bring it in. And have it. We're on a podcast, so probably the listeners wouldn't care anyway.
Yeah.
But yeah, it was pretty amazing because I don't think people realize this, but to get your science covered in the New York Times or any major newspaper is rare, extremely rare. To get it on the front cover, the front page is bizarre. I think you told me a lot of story about how you discovered that and you weren't expecting it to. Maybe we could just recap that before we get into the science. Like, how did you find out you were on the front cover?
Yeah, so it's Professor David Helfand here at Columbia introduced me to Dennis Overby when I told him that I had written this nice paper. And so, I described the science to Dennis, and he seemed very interested and convinced this is worthwhile, maybe worth kind of writing about. And then, communication with Dennis was sporadic for a few months. I met with him like in October of last year. We submitted the paper in September.
Yeah.
And then I get an email from Dennis. I'm in California. I get an email from Dennis like the day before I'm flying to AAS, the American Astronomical Society's annual conference in New Orleans. So he's like, they want to run the story today. And he had CC'd his two editors, senior editors, and I had no idea that he had written a story, much less, pitched it to his editors. And I had not seen the story. In fact, I would not end up seeing the story until it became public. So luckily, Dennis did a great job. But not luckily, he's amazing. So yeah, I'm at the airport Saturday morning, as I was telling you, getting ready to fly to New Orleans. I'm looking for the New York Times. I pick up a copy, and Dennis said it might be in print Saturday, Sunday, or Tuesday. So I pick it up, and I'm like flipping through the headers of the inside pages, like where's the science section? And I didn't see a science section.
Right.
So I'm like, okay, maybe it's not today. And then I start to put it down, but I flip the front page upside down. It turns out there's a beautiful collage of galaxies there. Yeah. That's the image that I sent to his editors. Like, this might be worth including with the story.
There it is.
And it's in color. And it says, the early universe may have gone bananas.
That's it's a great headline as well, I have to say. So it definitely catches people's attention. And so it's another food. We've got baguettes, pickles, and pizza pies, pizza Bordeaux, and now we've got bananas. So why don't you tell us what did you see? Where are the bananas coming in here?
Yeah, so the bananas. So I've worked closely with several people in SEERS and outside of SEERS for this paper, and a few of them are Haowen Zhang, a Finnish grad student at the University of Arizona, who I also worked with on some candles projects a few years ago, Santa Cruz, as well as Karthik Iyer, who's another Hubble fellow here at Columbia. Mark Huerta's company, Liz McGrath, Steve, and others. And so we were in my office just 2 doors down here, and we plotted, we took galaxies that were at redshift 2 and that had a total mass in stars that were a factor of 10 lower than the Milky Way today. So we think these were galaxies that were Milky Way progenitors,
Okay.
ancestors of our own Milky Way-like galaxies, 10 billion years ago. And we plotted we measured their projected axis ratios. So if you fit every galaxy on the sky with, an ellipse, you can characterize that ellipse by the ratio of the short axis, B, divided by the long axis, A. Kind of like when you're looking for a TV, you look at the aspect ratio.
Yeah.
And so you measure that for a bunch of galaxies, all these Milky Way progenitors, and you plot that on the y-axis of a plot.
So that's the rate. That's the aspect ratio.
That's the aspect ratio.
Okay.
So short axis to long axis on the y-axis.
A lot of axes.
A lot of axes, yeah. So aspect ratio on the y-axis of a plot, and then on the x-axis you plot how big is the ellipse, so the sizes of these galaxies. Okay. And when you make that plot for these Milky Way progenitors, it actually traces out a curved trajectory in the sense that as you go to larger size galaxies towards the right on the x-axis of sizes, galaxies are preferentially showing up towards the bottom of this diagram. So they're preferentially showing up with elongated or edge-on or flat or linear shapes.
So the bigger they are, the more pickly they are.
Yeah, exactly.
That's weird.
Yeah. And so when we made this figure with a particular color map choice, right, the higher density parts of this figure where all the galaxies were clustered in this diagram, it reminded us of the shape of a banana. And so that was the inspiration for the title of the paper, Galaxies Going Bananas, that in this diagram of aspect ratio versus size, these Milky Way progenitors 10 billion years ago are tracing out a banana in the sense that the larger size ones are preferentially have lower axis ratios.
So it's not that, I think that's a good point to clarify. It's not that the galaxies themselves are banana shaped, but that in this higher dimensional view of them that you're looking at, then you get this still very strange banana shaped.
A few of them do look a little curved, but there's probably a reflection of some other thing.
And that's really odd because I think you would expect, okay, even if things were pickle shaped at one point, presumably they have to get to a Milky Way shape at some point in the future. So you would maybe naively expect a convergence towards, in the deep past, for some reason they're pickle shaped. Then they go through the disc shaped, and that's kind of where they end up. But if they're getting bigger and more elongated, that's totally counterintuitive.
That's a very good point, actually. It is counterintuitive, and actually this connects to an exciting interdisciplinary area of galaxy formation known as galactic archaeology. So I've talked to people here at Columbia, including, for example, Katherine Johnston, professor here, and Emmeline Cunningham, another Hubble fellow, and they're archaeologists. And when I go talk to them about these results, they want to know, okay, how big were these pickles? I say that they're big, right? But really, in the early universe, things were denser, right? And galaxies were still growing. So these pickles in the early universe, in terms of, technical terminology, they were of order 1 to 2 kiloparsecs. Today in the Milky Way, we are 8 kiloparsecs away from the center of our own galaxy. So if these pickles survived, or whatever, they ended up at the centers of the Milky Way like systems today. So
they got absorbed then into
they got absorbed. We do see some of these galaxies, these elongated pickle-shaped galaxies, in some cosmological simulations. So these are simulations where you're trying to model everything in the universe, starting with the initial conditions of, the initial fluctuations in the density field of dark matter and baryons and so on, and kind of let it evolve under the influence of gravity, with some recipes, as we call them, another food analogy for how does stars form and how does gas cool.
You guys love your food.
Yes. We need to get our lunch before we start doing our research.
It's just a very passive aggressive way of saying give galaxy people more food.
Yes. Yeah.
But by the way, we had Katherine on the podcast, so anyone listening, if you've not seen that episode, please do check it out. And we get all into the anatomy of galaxies, which reminds me about bars. And and that's an obvious connection. So in the center of some galaxies, there are these linear-like structures which are called bars, and that seems like a pickle. Is that the connection then? At least maybe that's the connection you're hypothesizing, that they might end up as the bars of galaxies.
So I say this always, to whenever I'm giving talks about this to scientists and astronomers. So, you can call these early things bars because we do see like these, pickle shaped things locally. They're called bars, but in the local universe, these bars are found generally in massive disks, disks of stars, where the stars are dominating the gravitational potential. And so the stars in the disk can undergo these instabilities, dynamical instabilities, that then funnel them into this bar-shaped pattern. But when we look at these early galaxies that just look like linear structures in the sky, we don't really see, any evidence usually of a bright, aka massive underlying stellar disk out of which a bar could be forming. So the way these bars are forming in the early universe has to be probably very different from these like what we call secular, isolated bar, instabilities that happen in massive disks in the nearby universe. And there are ways to form these things. So some of these simulations that I mentioned that predict the existence of these elongated galaxies. Another way to form these things is to have mergers of galaxies along a preferential direction. So going back to the cosmic web connection, right? So galaxies form in the cosmic web, the skeletal backbone of the universe, and galaxies that we think are the progenitors of the Milky Way at these, distances and look back times 10 billion years ago, they're like the characteristic, lower mass systems. They form in filaments, filaments of dark matter. And it turns out from some of these simulations, these galaxies live in dark matter halos. And unlike the relatively roundish dark matter halo that the Milky Way lives in today, we think that these pickle-shaped galaxies, they lived in pickle-shaped dark matter halos. So the halos were also prolate ellipsoids. This has been known for at least 20 years, where, the first, lower mass, higher redshift, early forming halos tend to be more prolate because they're forming by accreting dark matter via mergers along a preferential direction dictated by the filament that they live in.
Okay.
And so this is very exciting because this actually has cosmological implications, and it provides a new observable way to test this whole scenario. So I wrote a paper in 2019 with Joel Premack and Sandy Faber and Avishai Deckel and Haowen Zhang and others, suggesting that if this story is true, that the nebular hypothesis does not apply in the early universe. Instead, the dark matter filaments are exerting their influence on galaxy formation, and that's why we're seeing all these elongated systems. Then actually we should expect to see on the sky strong intrinsic alignment signals, in the sense that these galaxies should not just be randomly oriented on the sky, these elongated ones. They should point towards one another on the sky.
Yeah, like iron filings or something.
Yeah, exactly.
The magnet, yeah.
Yeah, and they're tracing out filaments, the filaments in which they form over huge scales.
Wow.
And so this is very hard to do with like Hubble candles imaging, or even with James Webb, because the field of view of these telescopes is so small that even if you stack or tile a bunch of pointings, you're covering a fraction of the full moon.
Yeah.
But this is going to, I think, make a huge comeback. I'm trying to make it have it make a comeback in 2027 with the Roman Space Telescope. Because that, in a single pointing, it's going to observe 100 Hubble deep fields at once. And it'll be able to resolve these things, be sensitive to them over these huge areas.
Wow.
And so you can really start to redo my 2019 paper much more properly.
With way more statistics.
Statistics and actually look for these chains of.
So let's touch on the the legacy of candles and where this work fits in.
Yeah.
With candles, people saw these pickles. They weren't quite sure what to make of it. Some people believed it. Some people just didn't talk about it.
Yeah.
Now we have SEERS, JWST, essentially supporting that thanks to your work.
Yeah.
But also revealing these unusual trends. I think this banana trend was presumably not known before with candles, right? The fact that you get the more extreme aspect ratios with larger sizes. I presume that was not
So
known.
Haowen Zhang wrote a paper in 2019 using candles data suggesting this. And so he's my second author on this paper. So we collaborated on this. But even then, I mean, yeah, that was an extension of the earlier candles work by Arjen van der Wel, which people still didn't really, I think, didn't know what to make of it.
Okay. So people now, you think the community is coming round to it now because JWST is just so much more precise that it's hard to argue now at this point with the data? What's been the community reaction?
Yeah, so I think it's predominantly positive. People are interested. There's definitely been a few instances where some people are still concerned about the surface brightness detection bias, or the fact that, you know, these early galaxies, like the early universe, not only is it everything else I said earlier, it's also messy. Things are just undergoing mergers more frequently. And so if you have, like, how much of these elongated structures can you explain as just arising from mergers?
Right.
Not necessarily kind of telling us anything about the mergers happening along, you know, preferred direction via filaments and dark matter and cosmology, but it's just you have things smashing into each other, you have tidal debris, and then in projection you might see that always, you know, relatively be elongated.
Yeah.
So, but I think people are starting to, you know, I've been giving talks about this. I was traveling so much last fall. I just gave the Harvard colloquium last week, thanks to invitation by Avi Loeb, who initially also expressed some skepticism, but also has had a amazing number of beautiful ideas that we've discussed for, you know, ways to follow this up. So people are interested. People, I think, want to know the solution to this 30-year-old puzzle, you know, that was first kind of revealed and hinted at with the proto-Hubble deep fields. And now James Webb is just, and SEERS isn't even the deepest survey that we already have from, you know, there's other surveys. I've talked to people that are part of the JADES collaboration, which is another survey like SEERS
With JWST?
with JWST that goes even deeper. And I haven't had any indication from people telling me that, oh, actually, if we go deeper with JADES, we do start to see the disks around the pickle-shaped things.
Yeah, yeah.
So
then there'd be the bars almost, if that were
exactly,
true.
Yeah. But even if you see the disk, whether it's a disk of gas or stars, there's still something very strange, because typically bars and local disks, they're not the majority of the light or the mass. It's usually much less than 50%. But here it's like the underlying disk would have to be so faint or so large that it starts to become just as exotic as just saying these things are just pickles.
Yeah. So it sounds like we may have to revise our canonical theories of galaxy formation to not just think of these things as isolated pools of gas, as we've been sort of thinking, Laplace thought about it, but really embedded within this web of dark matter, that really that's the cause of this initial 1D structure. And then it is just fascinating that you go from 1D to 2D to 3D. Yeah. There's something, it seems like the universe is telling us something there.
Yeah. And there'll be lots of, you know, things. So we're thinking about ways to follow this up. So one thing that still we don't know, right, is for individual galaxies at these early times, like Milky Way progenitors that look like, you know, linear structures, for any individual one, we can't say with definitive certainty that, okay, this thing is an edge-on circular disk, this thing is an edge-on oval disk, or this thing is a pickle. Yeah. The way to tell that is actually to go in and get spectroscopy, very deep spectroscopy, and which then lets you constrain the orbits of the stars. Because nature has given us a way, I think, of distinguishing between these three scenarios, and that is that if it's an edge-on circular disk, which is the safe hypothesis, then the stars are going to be on circular orbits, roughly. So you should see, you know, one side is going to be blue shifted, one side will be red shifted in the rotation. You see a rotation curve. Yeah. But that's literally impossible if these things are highly elongated. Yeah. Because then the stars can't be on circular orbits. They have to be on a highly elliptical orbits.
Yeah, they're not moving back and forth towards you. They're just moving left and right.
Exactly.
Yeah. And so therefore there'll be no Doppler shift towards your perspective.
And so actually there's already a hint of this with one detection. People call it another food item, the hot dog galaxy. So there's a paper from 2009 by one of my former mentors, David Koo, along with James Lowenthal. And they actually they take one of these galaxies that look like an edge-on thing. It looks like an edge-on disk. It's one of the brighter, bigger ones. They put a slit on it, like a spectrograph slit, And then they ask, well, they go really deep. They use the Keck telescope to go really deep, and they were able to detect the spectrum, the continuum from the starlight, and then absorption lines in that continuum because of from the stars in that galaxy. And then they just ask, along the major axis, do you see the Doppler shift, red shift and blue shift on opposite sides? No signature of that.
Wow.
And so they concluded this is not a edge-on disk with ordered rotation. This might be a truly linear filamentary source that is maybe expanding or collapsing perpendicular to the line of sight.
Wow.
And so what I'm doing now, what I want to do with some of my collaborators, including David Koo and Sandy Faber and Joel and others, is do a proper census of these things with archival Keck data, Magellan data, maybe Hubble data. And then I want to start to think about having a large program, maybe take what I've learned from Steve, for example, and maybe try to PI a large program to get spectra of a lot of these things and take a proper census, how many to maybe, somewhat fainter limits, smaller sizes, look like disks edge on, but they're not because you don't see the rotation.
Yeah.
And if we can do that, then I think we can be more confident when we say, well, we might need to really, think about changing our standard picture of galaxies starting out as disks, merging to form ellipticals, and start to ask this question, well, where do the disks come from in the first place?
Yeah.
And how do you go from these 1D pickles to these 2D disks?
It's amazing how complicated these galaxies have turned out to be. And I guess what's fun is it's just fun to be in a time when the textbook is being rewritten. And somehow science is always more interesting when things are being ripped up and started anew. And you'll think, in 100 years, people will look back and think, wow, that was the period when they really for the first time, they realized the fallacy of that crazy nebula hypothesis. And they actually figured out what was going on.
And luckily, we're in the time also where we're only 10-ish years away from also a revolution in technology with the 30-meter class of telescopes.
Yeah.
So those are going to be able to do this kind of, get these measurements I'm talking about, like capture the velocity field of the stars, not just of the gas, across the face of these galaxies. It's going to be... Cool. I wish it was going to happen tomorrow, but I'll have to wait 10 years.
Not too far. At least it's in our career path. Yeah. And the last thing I wanted to sort of touch on with this scientifically was the dark matter aspect.
Yeah.
So if we think dark matter is guiding the shapes of these pickles, the shapes of these galaxies, can we flip that around and use that to learn anything about the dark matter? And in particular, there's a couple of ideas about what dark matter might really be. Of course, no one has a sample of it in a test tube anyway, unfortunately. Trying to, but we don't have anything yet. And so one idea is that it's just this cold dark matter, like a WIMP-like particle, often called like a very heavy particle. But another idea is that it's fuzzy, and it's this axions. They sometimes call axionic dark matter, which is almost like a wave, and it's behaves a little bit differently to the clumpiness of cold dark matter. So does the existence of these pickles tell us anything about which model might be correct, or all bets still on the table with that?
Yeah, that's a really good question. So I think we would all wish it told us something about the nature of dark matter, because that's a fundamental physics question, and we want to try to use galaxies to get a handle on fundamental physics. The problem is that what we observe are the galaxies, and the galaxies are the result of very complicated, these baryonic processes, like how gas cools and accretes, gets blown out because stars explode and black holes form and so on. And understanding that is crucial to interpreting what we observe, in like JWST observations. And I don't think we understand that well enough yet. But suppose we did understand that well enough, then the connection to dark matter is interesting. And I've talked to people about this, people that work on alternative dark matter models, because there are many issues with cold dark matter, right? So one of the motivations for trying out warm dark matter that's slightly faster moving or lighter, or axionic dark matter, or self-interacting dark matter, where the dark matter can actually undergo some collisions, is because we have all these puzzles such as nearby, cold dark matter predicts many more small mass galaxies than are observed, like around the Milky Way, for example. Or cold dark matter predicts that as you go towards the center of any individual galaxy, the density profile should continue to rise and rise and rise. Whereas what the observations show is that actually the density profile flattens off.
Yeah.
A core is in the center of many galaxies. And this could be a new puzzle. This could be, you know, there's pickles in the early universe. Can you form pickles in a cold dark matter paradigm? Mm-hmm. So current indications are you can form pickles. I mentioned the simulations by Joel Premack, Avishai Deckel, Daniel Severino, and collaborators, where they're very high resolution simulations. It's a standard lambda CDM cosmology with very reasonable prescriptions for the baryonic physics. And this is where the story comes from, that these galaxies that are pickle-shaped, they live in pickle-shaped halos that are then in filaments, and mergers are going along one direction, which stabilizes their pickle shape.
Okay.
But what we don't have yet, is larger volume simulations that can resolve down to the scales of these small mass, small size, distant early universe galaxies. Because what I really want is statistics. Mm-hmm. You know, in a cold dark matter paradigm with reasonable variations on baryonic physics, maybe, how many of these things do you expect? Pickle-shaped galaxies in the early universe. You know, our observations with JWST, they suggest that the majority, 50 to 80% of Milky Way progenitors in the distant universe may be pickle-shaped in 3D. But in some of the best simulations that we have right now, which don't have the resolution, I think, so it's hard to draw any claims of the baryonic properties of the galaxies, but they predict like pickle shapes of maybe 10 to 20% at most. And so I'm working with a lot of people to think about running higher resolution simulations, you know, within a standard lambda CDM, reasonable baryonic physics, to see, well, under what conditions can these things form? And are they actually found in cosmic web filaments? How are they oriented? You know, to kind of test our mental model.
Yeah.
And it'll be exciting, you know, to then think about alternative dark matter simulations. People are doing that, you know, highly respected groups are pursuing this, but it's just very hard to disentangle the galaxy formation physics with the fundamental physics of cosmology, the nature of dark matter and dark energy, and so on.
So don't hold your breath for an answer on that just yet.
Yeah.
But what, you know, maybe just to finish this off, what is the next thing, if people who are following this story and are interested in early galaxy, the mystery of them, what is the next thing we should be on the lookout for that you're working on or a big team's working on that will hopefully add some new information to this story?
Yeah. So I PI'd what we call a legacy proposal. So every year NASA puts out a call for proposals for people that want to do science with James Webb and Hubble and other telescopes. And so I PI'd a large one, a legacy proposal, with a large team, including Steve and many others. And the idea here is we're going to take all of the data from James Webb that was collected in the first 2 years, that's going to become public this April, and we're going to have a much larger sample size of galaxies over many different parts of the sky. And we'll try more sophisticated 3D geometry modeling approaches to kind of go back and double check, you know, what we did with SEERS. And we'll come up, we think, with candidates, these elongated pickle-shaped candidates that we can then pursue follow-up spectroscopy on. So I think the next big thing people should look out for is results from spectroscopy. So what is the velocity structure of the gas in these pickle-shaped candidates? And we hope also some first constraints on what are the orbits of the stars in some of these things.
Because that'll finally tell us whether they truly are pickles.
Because that will tell us for any individual system on a case-by-case basis, smoking gun. Like, okay, this thing looks like an edge-on disk, but there's no rotation of the stars. So it's not. And now we have to then make the case for getting other kinds of data, maybe looking for second order effects.
Yeah. So it looks like a duck, but you want to see if it quacks like a duck.
Exactly.
And
Yeah.
we've got a
Yeah.
duck. Okay.
Yeah.
Well, Viraj, this is very exciting research, and thank you for coming on and telling us about it. Maybe we'll have you on in the future when you have some more results for us, because this story is obviously one of those ones that's evolving and in play, and maybe next time in the front of the New York Times, you'll be here again. I don't know, but this is amazing that the public are so engaged with it as well, and I hope those listening enjoyed this. So thank you for joining me today.
Yeah, thank you so much, David. Yeah.
So that was my conversation with Dr. Viraj Pandya. I hope you enjoyed it. I know for me, what I really enjoyed and took away from that conversation was the sense of excitement and revolution that we are still in. It sometimes is a little bit deflating, quite frankly, when you look through science textbooks and you learn about how the world works, the universe works, how galaxies are made, stars are made, and it kind of seems like we've figured it all out. And so when you come across something like this that just totally rips up the textbook and says, no, go back to, the chalkboard and figure things out right from the beginning again, it's invigorating, it's exciting, especially if you're someone just starting your science journey, a research journey. These are the kind of fields that I think you would be drawn towards, these big open questions that are just revolutionizing and challenging our canonical views of galaxy formation or whatever it is. So I'm certainly very intrigued to see how this story plays out. It's obviously still kind of early days. We had this early data from HST that hinted at these pickle-shaped galaxies. JWST seems to be supporting them thus far, but still only the early release data. But we've got 10, 15, maybe even 20 years of JWST to look forward to. So this story will be resolved one way or the other. I'm confident of that. And if these things really are pickle-shaped, then we're going to have new textbooks to print, right? And that's incredibly exciting. And I suspect it will be true of so much of not just how we understand galaxies, but many of the fields of astrophysics as well. Isn't that amazing that every time we build a new telescope that is an order of magnitude more sensitive than that which we had before, it completely transforms our view of the universe, and everything that we thought we knew turned out was just an approximation or even just a complete fallacy in some cases. It makes you wonder how much of what we currently take for granted as factual, as canonical, as this is true, how much of that will eventually be ripped up in the balance of new information that will come in and show us that those early thoughts were maybe even childish in terms of how we thought about the universe. And that's kind of exciting. That's kind of exciting to think the story is still being figured out and we are actually a part. We are the architects of that evolving story. So I really enjoyed that conversation. I hope you did too. If you want to support what we do here on the Cool Worlds podcast, we don't have sponsors, right? This is just me in front of a camera, getting a guest on, and we're just doing this for you guys. There really isn't much other reason for doing this. But if you do want to support what we do, the best way is, of course, do all the subscription and share. I mean, that generally does make a big difference. But if you are serious and you want to add some monetary benefit to what we do, then probably the best thing to do is to support my research team, the Cool Worlds Lab. So I'll put a link down in the show notes where you can see how to do that. But the link is coolworldslab.com/support. That is a way which you can become essentially like a Patreon to not even the development team of these podcasts, but actually my research team. 95% of that money goes just to research. There's a very small 5% credit card fee that the university takes, but 95% of that comes to my research team, which we use to support students, write new papers, do exploration of new ideas. And of course, the more research money that we have in the team means the less time I have to writing proposals. And so that gives me more time to make these podcasts. So there really is a strong synergy there. And I kind of like the idea of you supporting research rather than camera equipment or anything like that. So I think that's the best thing for you to do if you really want to support us. So check that out. That's coolworldslab.com/support. And until the next episode, stay thoughtful and stay curious.